The Gulf of Mexico does not warn you. On September 8, 1900, it came without a forecast, without ships turned back in time, without anything standing between the people of Galveston, Texas, and 17 feet of storm surge rolling off open water. Somewhere between 6,000 and 12,000 people were dead when the sea pulled back. An entire city of 38,000 had been scoured across a flat barrier island with no natural high ground, no ridge, no hill of any kind between the city and the Gulf. Bodies were burned on the beach because the numbers were beyond what the living could manage any other way. Galveston had been the fourth largest port in America. It had been called the New York of the Gulf. Editors in competing cities published arguments that the city should be abandoned entirely and the port relocated somewhere the Gulf could not follow. The case had force. A flat barrier island sitting barely 8 feet above mean sea level at its highest point has no natural defense against a storm capable of raising water 17 feet above that line. The city decided to stay. The answer it committed to was a wall of reinforced concrete, engineered in sections and poured by hand into barrier island sand, in an era before power concrete mixers, before hydraulic cranes, before any machine capable of driving a pile into open beach. If this story is touching your heart, take a moment to hit that like button and subscribe. Drop a comment and let me know where you're watching from. And if a woman in your family came west with nothing and built a home, share her name in the comments. I read every one. 3 engineers were appointed to design the wall in 1901. Henry Martyn Robert, Alfred Noble, and Henry Rowe formed the board charged with producing a design that had no real American precedent. Robert had spent his career in the Army Corps of Engineers and was better known outside engineering circles for a parliamentary procedure manual he had published decades earlier, the same manual that still governs formal meetings across the country. Noble was among the most accomplished civil engineers of the period. Together they faced a technical problem that drew from European harbor construction experience but had to be adapted to conditions none of those precedents had addressed. Soft Gulf barrier island sand, the load signature of a direct hurricane strike, and a civic budget stretched thin by the storm they were designing against. The wall they specified was not a flat-faced structure. A vertical plane struck squarely by a wave transmits the full energy of the impact directly into the wall and the foundation behind it. Their wall would have a concave front surface, curving inward from the top down to the base, calculated to deflect incoming wave energy upward and outward rather than absorbing it through mass alone. The deflected water would rise above the coping, lose its energy in the air, and fall back without the forward momentum needed to reach the city. Every foot of that concave curve had to be poured consistently across the full run of the structure. A section formed incorrectly would deflect differently from the sections beside it, and the seam between inconsistent sections is a seam waiting to fail under load. The foundation specification called for creosote-treated timber piles, 20 feet long, driven to a depth that would resist scour. Scour is the mechanism that takes down seawalls from below. A surge wave strikes and pushes water inland, then the pressure equalizes and the water rushes back off the beach, carrying sand with it. Repeated cycles of strike and retreat erode the material from beneath the foundation. The foundation settles unevenly and the wall above it begins to separate. Deep piles were the only counter the engineers could build into the design. Steam-powered pile-driving rigs moved along the planned wall line beginning in 1902. The operating principle was unchanged from decades of prior use. A heavy iron drop weight lifted by steam-driven cable, released and allowed to fall onto the head of the pile, advancing it downward one blow at a time. Workers set the leads, guided each pile into position, monitored penetration rate, and managed the steam engine. The line moved forward one pile at a time. The pace had to stay ahead of the form-setting crews that followed. With piles set, workers erected timber forms along the wall line. These forms were the mold, and their geometry had to be held precisely through the entire pour. 16 feet wide at the base, 5 feet wide at the coping, 17 feet of total height from the beach grade up. The concave front face required curved formwork, rigid enough to hold its profile under the pressure of wet concrete being poured against it. Any warping in the form transferred directly into the finished wall. Concrete, once hardened, cannot be reshaped. An inspection of the form before the pour and a watch through it was the only window to catch a problem before it became permanent. The men who built the seawall were day laborers, concrete workers, pile-driving crews, and dredge operators drawn from the regional labor pool of the Gulf Coast. Wages for common labor ran between 80 cents and $1.25 a day. The work was exposed on open beach with no overhead shelter, in Gulf Coast summer temperatures that regularly run above 90 degrees. Concrete work under direct sun means moving heavy material through the same heat that the curing concrete itself generates around it. The inspectors and foremen, making daily decisions about materials and methods, were solving problems that had no ready American precedent to draw from. Portland cement arrived by rail and barge. Aggregate was sourced locally and hauled in. Steam-driven drum mixers combined the components. No pump capable of moving wet concrete any useful distance existed in 1902, which meant every cubic yard of concrete that went into the wall traveled by wheelbarrow or hand bucket from the mixer to the open form. The initial section of the seawall was 1.5 miles long. At 16 feet wide at base and 17 feet tall, the volume of material required to fill that form runs into tens of thousands of cubic yards. The arithmetic of how many wheelbarrow loads that represents, across how many days of sustained labor on exposed Barrier Island beach, describes the actual work more accurately than any summary can. Construction joints between poured segments were the wall's critical vulnerability. New concrete poured against old concrete that has passed its bonding window creates a cold joint, a plane of weakness at the seam between two structural sections. The engineers specified procedures for managing each joint and built the pour schedule around those requirements. A cold joint in the finished wall would not show at the surface. It would reveal itself only when a storm applied lateral load across that seam. The wall alone was not sufficient. The engineers understood from the start that 17 feet of concrete at the waterline would protect the blocks immediately behind it. The interior of the island sat at the same low grade that had made the 1900 surge lethal everywhere it reached. Storm surge does not stop at the back of a seawall. It finds drainage channels, low streets, and every depression in the grade, and pushes inland wherever the elevation falls below the surge level. Building the wall and leaving the island's interior at sea level would redirect the water, not stop it. The solution was to raise the grade of the entire city. The plan called for hydraulic fill across roughly 500 city blocks. Dredges moored in Galveston Bay and in the Gulf would cut sand from the sea floor and pump it as slurry through a network of temporary pipes laid through city streets. Where the slurry settled and dried, it became solid fill. The dredges ran continuously when conditions allowed. The pipe network required constant maintenance because sand slurry is abrasive and will erode pipe joints under operating pressure. Workers walked the pipe routes monitoring flow, listening for the sound change that indicated a developing clog ahead of a full shutdown. Before fill could be pumped around any building, the building had to be raised above the target fill elevation. Workers built timber frameworks beneath each structure, threading heavy beams under foundations and distributing load across hundreds of bearing points. Mechanical jack screws were positioned throughout each framework. On a signal, workers on every jack turned simultaneously, advancing the structure in fractions of an inch and checking level at each increment to keep the load balanced. Fill was pumped beneath each raised structure as the sand settled and hardened. Then the framework was removed and the operation moved to the next address. If you're still with us on this porch, do this story a kindness. Hit subscribe and turn on the bell. These quiet stories don't get told if you don't share them. Tag someone who loves a true frontier story in the comments. Let them know we're telling these the way they deserve to be told. 2,156 structures were raised across the fill zone. The tallest lifts ran to 17 feet. Hotels, churches, commercial buildings, and private homes. A convent that engineering records describe as weighing 3,000 tons was raised without cracking a single wall. The city operated continuously around all of it. Businesses stayed open during the raising. Residents remained in their homes while jack screws turned beneath their floors. Streets were blocked, filled section by section, rebuilt and reopened. Water and gas connections were extended upward to meet the new grade. The whole operation took years. The The pace of the fill work was tied directly to both the dredging capacity and the Gulf's hurricane calendar. City leadership and the engineering board understood that storm seasons continued regardless of construction progress. A partially raised grade with a fill front that stopped short of the next block left an exposure exactly where the protection ended. Contractors and supervisors were managing a construction timeline set not by any administrative schedule, but by the probability of the next Gulf storm. The construction risks were constant and physical. Pile-driving crews worked on the Gulf-facing side of the wall line throughout the active storm season months. The seawall rose to 17 feet above the beach, which meant the top of the form was a fall hazard with no margin below. Concrete work in direct Gulf Coast sun ran workers through heat exhaustion at a steady rate, and stopping a pour midway through a section because of incapacitated workers meant creating a cold joint at an unplanned location. Managing the pace of the pour and the physical condition of the workforce were the same problem. The grade-raising frameworks presented a different category of hazard. A timber structure carrying the weight of a large hotel or church across a field of jack screws and bearing beams is under tension at every point. A single failure in the framework, a bearing that shifted, or a jack that lost its seat, could transfer load instantly to adjacent points. Workers inside and around those structures during lifting operations watched the framework continuously and responded to any sign of uneven movement before it cascaded. Inspectors worked through each lift. The pipe network added a third risk. A pressurized slurry line failing at a coupling in a city street released pressurized wet sand at the break point. Workers near a failure had to clear the area before pressure equalized. Repairs required shutting pressure to the affected section, locating the failure point, and restoring the joint while the pipe remained packed with wet, abrasive material. The dredging itself altered the bay floor in ways no one tracked in real time. How the removal of that volume of sand from Galveston Bay affected tidal patterns and sediment dynamics was a question that contemporary engineering practice had no tools to answer. The first real test came in 1905. A Gulf storm drove surge against the new concrete before the grade raising was complete. The wall held. Water climbed its face, threw spray over the coping, and retreated. The street behind the finished section stayed dry. For a city that had burned its dead on the beach 5 years before, watching water stop at a line of concrete carried a weight that no engineering document from the period adequately recorded. The harder test was 1915. A hurricane approaching the intensity of the 1900 storm made landfall on the Texas coast. Surge at Galveston reached 12 feet above mean low tide. Communities along the coast without seawall protection were flooded in the same pattern that had destroyed Galveston 15 years earlier. 8 people died in Galveston. The estimate of dead in the 1900 storm runs from 6,000 to 12,000. 8 people in a storm of comparable force is the number that answers the engineering question more definitively than any structural analysis can. By the early decades of the 20th century, the wall began to be extended. Each new section followed the original specifications without modification. The concave face geometry, the foundation depth, the pour and joint procedures, all carried forward because the original calculations had been right, and subsequent engineering review found no reason to depart from them. By the time major extensions were complete, the wall ran more than 10 miles along the island's Gulf shore. The Galveston project established a pattern that shaped coastal protection planning in other American cities facing similar vulnerabilities in the decades that followed. The combination of a seawall at the waterline with a raised interior grade, the two elements working together, was the conclusion the Galveston engineers had reached under pressure. Gulf and Atlantic coastal communities, studying flood protection after major storms, looked at what Galveston had built and how it had performed. The logic of the design became the basis around which subsequent American coastal protection planning was organized. Modern construction tools arrived in stages. Concrete pumps replaced the wheelbarrow chain. Diesel pile drivers replaced steam drop hammers. Structural analysis moved from hand calculation to computation. Each change improved speed and precision. What did not change was the physical logic of the wall. The workforce that builds such a project today arrives with machinery that can complete in weeks what took years of sustained hand labor, but it measures results against the same fundamental principles the Galveston engineers arrived at by building the wall and watching what happened. A wall must deflect load, not just absorb it. The foundation must run deeper than the scour can reach. The joints must bond, or the wall will fail at exactly the moment it is needed most. Hurricane Ike came ashore in 2008 as a Category 2 storm, but its physical size gave it a surge capacity out of proportion to its wind classification. Along sections of the Texas coast without seawall protection, surge reached 20 feet. In Galveston, behind the wall, flooding occurred, but the clearing scour that Ike produced to the east of the wall's end did not reach the protected zone. Aerial imagery taken after the storm showed the boundary clearly. Where the concrete ended, the storm's record on the landscape changed. 10 miles of differential outcome made visible from the air at the line where the seawall stopped. The structure that absorbed Ike was poured by workers earning roughly $1 a day in 1902. The concave face still visible along the Galveston seawall is the same geometry that Robert, Noble and Rowe calculated from European harbour precedents and adapted to a Gulf barrier island where nothing like it had ever existed. The creosote-treated piles beneath the concrete were driven by steam drop hammers into the same barrier island sand where the 1900 storm had covered everything and reached everyone it could find. The steam rigs used to drive those piles are gone. The temporary pipe network that routed fill slurry through 500 city blocks was dismantled when the grade work was complete. The timber frameworks and mechanical jack screws that lifted more than 2,000 structures have long since been broken down. The men who pushed those wheelbarrows across open beach in August, who turned those jack screws beneath church floors, who walked pipe routes listening for the sound of a failing joint, are gone. The wall is still there. 120 years of Gulf storm seasons have come against it. What the workers poured by hand into timber forms on a strip of Barrier Island beach is still holding water back, still deflecting wave energy upward along the same concave curve that 3 engineers drew in 1901, still doing exactly what it was built to do. Thank you for staying until the last word. If this story moved you, the next one is already up on your screen. Go give it a watch. And if you haven't yet, subscribe and join the porch. We're telling stories about women who carried more than the world ever knew. See you in the next one.